Okay, so now that we have looked at this doubly stochastic matrices, we looked at the stationary distribution of two different but linearly structured random walks. Let's generalize now to arbitrary graphs. Let's recall one thing that we already looked at in the lectures on random walks. We proved that we first of all defined something called the cover time, and the cover time is basically the maximum over all the possible starting vertices S. So that's the set of all, V is the set of all vertices. The expected time for a random walk to visit all nodes starting from S. Um, so now if you have a graph and this is one candidate, one vertex, start a random walk from that vertex and you ask what is the expected time to cover or see or touch all other vertices. So, but that would be just for that one vertex. Now what you'd have to do is consider that expected time for all vertices and then take the maximum over all the vertices, and that would be the cover time. And in the lecture, we actually showed that the cover time for a non-bipartite graph is at most 4mn, which is nothing but O of n cubed, where n is the number of vertices and m is the number of edges. And if you recall, the key intuition for the proof was to look at this graph and so here, if you look at an edge in this graph, and let's say this is vertex u and this is vertex v, and now let's say you start a random walk from u. What we first showed was that the expected time for a random walk to go from u to v is at most 2m. And, and then to complete the proof, what we did was we considered a spanning tree of this graph, and then we argued that we could cover the spanning tree in at most 4mn time steps. So that was and we used, if you recall, we used linearity of expectation to do that. Now the interesting question, and this is a question based on exercise 7.24 of the Mitzenmacher and Upfall textbook. So we know that the upper bound on the expected running cover time is O of n cubed. And if you look at, for example, the complete graph so the complete graph on n vertices, the cover time there is just O of n log n. So some graphs have very high cover time, very fast cover time. And this, if you recall, you may want to prove that this is in fact correct. And I just want to remind you that this is somehow connected to the coupon collectors problem. So with that being the case, the obvious question now is O of n cubed upper bound of the cover time really tight? In other words, is there some bad graph for which the cover time is indeed big omega of n cubed? And as it turns out, it is in fact tight. And interestingly, the graph that displays such a large cover time has this very nice structures called the lollipop graph. The lollipop graph has two parts to it. There is the complete graph part, which is especially in about half the vertices are all completely connected to each other. So this is the k and n by 2. And then we have the handle of the lollipop, which is another n by 2 vertices, but now connected linearly. Now, let's try to think about why this is in fact the case. Now, Let's for the moment ignore the complete graph part of the lollipop. And one way to do that is just say that let's say you start a random walk at this vertex v, and you ask, okay, how long does that random walk take to reach u? And this is a question that we've already discussed in the lecture, and that recall will take theta of n squared. Okay, so um, on expectation, of course. So now, why does the whole graph? So, for example, if you start at v in theta of n squared time, it will reach u. And once it reaches u, we already have seen that the complete graph has a cover time of just O of n log n. So once it reaches u, the random walk will fall into this complete graph, and the entire graph will be covered in an extra O of n log n time. So, um, so the question therefore is, why are we making this claim? And the reason for that is that in the definition of the cover time, you have to not just consider any one vertex as a starting point. You should consider every vertex as a starting point, and then compute what is the worst cover time. So let's actually, instead of starting at v, let's start at some vertex inside the complete graph part. Okay, so let this be our starting vertex s. Now, what will happen is that um, this random walk will start walking around this graph, and at some point it will have to come to u. Okay, and then somehow make its way all the way to v. What makes this challenging is the following. So if it comes to u, then there's actually a good chance that it will fall back into this complete graph part. So, and as long as it's inside this complete graph part, it's going to be making random walk steps inside of this region, and only with probability 1 over n, it's going to come to this vertex n. And then from this vertex, even if it were to make a few say a transition like this, then with some good probability it will come back here, and then it could still fall into this complete graph part. So the random walk, in some sense, can easily get stuck in this complete graph part, and then it takes a lot of effort for it to leave this complete graph part and then move all the way to v. Even if it were to make a few transitions, it could with some reasonable probability, and you can think about it intuitively. And I also encourage you to write a small program to actually verify what I'm claiming here. It could then easily fall back in here. So really, to work its way all the way to v is takes some effort, and that's where this big omega of n cubed comes in. So let me give you a little bit more intuition as to why this is actually n cubed. So now, as just assume that we are starting at s. Well, actually, let's not do that. Let's in fact ask ourselves, consider what happens when we say are here. Suppose we started at s and we've reached over here. Now we want to know what is the probability that this random walk that has reached this vertex, let's call this vertex u prime, let's call this u, this is v. What is the probability that the random walk will reach v before it reaches u? So the event we are interested in is so the random walk starting at u prime reaches v before reaching the vertex u. And we are interested in understanding this probability. Okay. Now, this can be actually understood reasonably easily. It takes a little bit of effort to see. I mean, not effort, but just a little bit of thought to see this intuition. Now, from u, you're equally likely to go from u to u. Let's consider this as u double prime. From u, let's see whether we will reach u first or u double prime first, and that's a symmetric random walk. So these are two symmetric events, so their probabilities are equal, and so with probability half, the random walk will reach u prime. Okay. Now that you've reached u prime, now ask the question: will we reach u first, or will we reach this vertex, say u star? Okay, and this again, these are two symmetric events: the event of reaching u or the event of reaching u prime, u star. So that again, the probability that you go here before you go to u is again another half. So what you can see is that with probability half, you will reach u double prime before u, and after having reached u double prime with another probability half, you will reach u star before you reach u, and so on and so forth. If you think a little bit and work out the mathematics, you will realize that with probability 1 by 2 raised to the something like log n by 2, you will reach v before you reach u, and working through that should help you reach this goal of showing that the cover time for this graph is in fact big omega of n cubed.